Welcome everyone. In this lesson, we're going to see how to use definite integrals and actually a little bit of geometry to help us calculate the net area and the total area for the region between a curve and the x-axis. So we're going to start seeing some applications of the definite integral here. And actually, this is a really good way. Area calculations are a really good way to start kind of help us conceptualize what the definite integral actually is. So that's what we're working our way towards. We're going to start really investigating what these definite integrals actually do. All right, so first of all, let's start with just some important definitions. And that has to do with the region under a graph. So when we say the phrase area under the curve, what we're really referring to is the area of the region that's bounded above by the graph of our function f of x. It's bounded below by the x-axis. And then it's bounded on the left side by some vertical line x equals a. And it's bounded on the right side by some other vertical line x equals b. So if we have this function here, say f of x, an example might be to calculate the area under the curve from x equals 1 to, say, x equals 3. And so we're dealing with this region here, where the bottom of this region is the x-axis. The top of the region is actually the piece of our curve, f of x. And then we have our right side, we have our left side, and these are just vertical lines. In this case, x equals 1 and x equals 3. And then we also have just the bottom of our region. And that's just a portion of the x-axis. So we have this kind of rectangular-ish region where the top side is actually part of our curve. And then the left, the right are vertical lines, and then the bottom here is part of the x-axis. So this is an example of what we mean by area under the curve. It's the area for this region bounded above by our function and bounded below by the x-axis. Now, one little important thing to note here is for this interpretation, our function f has to be continuous on the closed interval from a to b. So we don't want any jumps or breaks or kind of holes or gaps or that kind of thing in the top section here. Sometimes we can deal with that, but for right now we're assuming our function is continuous. And for right now, we also assume that our function is non-negative. And what we mean by that is it's actually above the x-axis. It's on or above the x-axis. So non-negative means f of x is greater than or equal to 0. Or another way to think of that is that the graph of our function here never goes below the x-axis. We will see how to handle, for area calculations if the graph does go below. But for right now, we're just assuming that our function is nice and above the x-axis. Or maybe it touches it, but for the most part, it's above the x-axis. And so what we're doing is we're going to answer the question, how do we find the area of this shaded region? That's kind of the motivating problem here, is how do we find the area for this shaded region? And it turns out, pretty surprisingly, that it's the definite integral. So let f be a continuous non-negative function on the closed interval from a to b. The area under the graph of f from a to b, that area, is equal to the integral, the definite integral of f of x from a to b. So this is pretty remarkable, actually, that if we integrate the function, if we calculate this definite integral, what we're really doing is we're calculating the area under the curve. Now, one important thing here is, like we said, there's kind of two conditions here. Continuity, we don't want any jumps or breaks in the top side of our region. Sometimes we can deal with that, but that's more of a problem for Calc 2. So we're going to be assuming our function's continuous. But really, for our purposes, this non-negative condition is important. So this, we want to really emphasize this. This formula only works if our function is non-negative. So it can't go below the x-axis. So it's on or above the x-axis. So if our function stays on the top half of the xy plane, we're good. We can calculate the area under the curve. All right, so let's try a few examples of this, just to see how this is working, and just to kind of get, some actual sketches of actual functions and regions under the curve. So we'll see it for the first example next.